glad you could join us today for our monthly GPSX webinar. Today I'm going to be talking about characterizing your Influent wastewater stream in GPSX. So this is obviously one of those things that's an important step in putting together your model and going through the calibration process. And we have some special tools that we've built in GPSX to help you out with that. And it is something that we do get questions about on a regular basis, and is also part of our regular training package that we put together for people who have purchased GPSX, or if you're looking to get a refresher on how to use GPSX, that is one of the things that we do talk about on a regular basis. So as per usual, please feel free to enter any questions that you might have while I'm going along in the chat. And what we'll do is I'll hang around at the end of the webinar and answer as many of those as I can. So to get things started, my plan for today is to talk a little bit about Influent characterization, what I mean by that, why it's important, what the steps are that you have to go through. I'll talk a little bit about the models that we have in GPSX and how they are set up so that they can help you do the best and most efficient job of characterizing your Influent, and a little bit about the data that you might collect and the data that you might have and some of the issues with that data that you typically encounter. As with any modeling project, the data is never going to be perfect, and so I'm going to talk a little bit about common problems that you might run into. So I'm going to jump right in at that point to talk about the Influent Advisor tool. That's the menu that you use to enter in your Influent information, and it's got a lot of software features in there to help you manage the data and understand what you're looking at. And then also some little bit of work around the idea of doing that over a dynamic data set. We have a special tool for that. And of course, as usual, I'll be doing a couple of desktop demonstrations to talk about those things. And as I mentioned, I'll stick around at the end and answer any questions that you have. Okay, so to get started, what is Influent characterization and why is it important? Well, basically, Influent characterization refers to specifying the concentrations and stoichiometric ratios of various components in your Influent stream. So anytime you set up a GPSX model, you have to have the starting point of your wastewater that's coming in. And most of the time you'll be using this object here. And when you're doing that, you have to enter in what is the flow and the pH and all of the concentrations of all those various kinds of components. And so it's important to get that set up well and get it set up in a way that makes sense for the model and for the data that you have. And it's really a key component of calibrating your GPSX model. So as we'll see, adjusting some of the stoichiometric ratios for which you don't have a lot of data can be a way to calibrate the performance of your model. So, excuse me, as you will see, adjusting the relative biodegradability of the COD that you have measured will have an effect, of course, on the model itself. So it is sometimes one of the more challenging steps in the process of setting up and calibrating your model, though, to do all the debugging and making sure all the information that you're using has been accounted for and is sort of working for you in the way that it needs to. Right. Influent characterization is important. It's basically the beginning of the overall mass balance of COD, nitrogen, and phosphorus across your whole plant. So as you know, these ASM models, they're based on those fundamental components, and we're trying to do a mass balance of different kinds of COD and nitrogen and phosphorus. And so you have to tell the integrator, the solver there, like what is the amount that's coming into the plant at the beginning. And therefore, that influent that you have set up, it really drives the rest of the model, everything going downstream. So, the mixed liquor and the sludge production and so on are going to be, at least to a certain degree, a function of what you set up in the influent. And so often adjusting your influent is a way that you go about calculating and calibrating your model. And it's always a step in the process because we never have all the information that we need. Even if you have a very detailed sampling campaign, it doesn't give you data as well in as fine, discretization as what the model needs and understands. So there's a series of calculations and or assumptions that we have to make to get from what you have to what the model needs. However, That is sort of standard practice. That's what we've been doing in this modeling technology industry for 30 years. And it works great. Everybody sort of, has an understanding of how these things come together, and so setting up and characterizing your influent is part of that process. So just to summarize that last point is basically to say that the models themselves are quite sophisticated in what they're trying to do with the information that you're giving it, and just leaving everything at the default on your influent kind of defeats the purpose of setting that thing up. So for the most part. Okay, so the good news, I know that all sounds like, oh, what are we going to do now? The good news is that we have a bunch of tools that we have put in place inside our software to help us do our job, and one of those is Influent Advisor. It is in fact the menu where you enter in everything, and if you've built a GPSX model before as part of our tutorials, or if it's part of your regular work, you have of course opened up this menu and entered in a bunch of information into it. And even though it kind of can be overwhelming about all of the stuff that we present here, we've tried to design it in a way that highlights when you have problems. It tells you what is going to be going on in the background before you have to even build your model and get things going. So it's designed to be both the way you enter in your information, as well as a screening and debugging tool, kind of all built together in one place. So it does look like a spreadsheet, of course. And in fact, when I joined Hydromantis years ago, Influent Advisor was actually a spreadsheet outside the software. And then we put together this tool inside to basically perform the same purpose and allow nice, easy exchange of information. Right. Okay. So let's talk a little bit about the influent models that we have. Those are the things that calculate what the model needs from the data that you have, and a little bit about the data that itself. So these ASM type models are really built around the concept of doing a dynamic mass balance of a set of components that represent the constituents of the wastewater. So this is the individual types of COD and nitrogen and phosphorus that I've mentioned before. And there are a very wide number of these. Now, if I just pick the very simplest model of all, ASM1, it has 13 state variables that are made up of COD and nitrogen only. There's no phosphorus in ASM1, and then also an inert state variable as well. So we need to know what are the concentrations of those at the beginning of the model as they come in. And the tough part is, of course, when the model wants to perform all the transformations in the bioreactor, saying, we're going to use up a certain amount of a substrate and then produce a certain amount of biomass as per this matrix, if you're more used to seeing the matrix format of a model. We need to have a good measurement of what those are. So here they are. These are the 13 state variables that exist in ASM1, and we need to set up our influence so that the model will know what all these are coming in. The main problem is that we don't measure these things directly, right? We just normally have some sort of what you would call composite or bulk measurements of kind of a bunch of those state variables combined together, right? We have a TSS number. That's like the sum of all of the particulate stuff. We have a total COD number or a total BOD number, but usually not both. So we're measuring some amount of organics, and maybe it's only the biodegradable part or not. We have TKN. We have maybe soluble COD. Sometimes I get that number for my project, sometimes I don't. Then probably we'll have a total phosphorus or maybe a soluble phosphorus. We only have usually 5 or 6 numbers that we might have coming in. And even those are kind of, they're not measured most of the time in a continuous way. They're measured as a composite sample or even a grab sample, intermittently, like on, Tuesdays and Saturdays or that kind of thing, right? So it's an incomplete picture, but it's the best we got. So, and of course, we have a whole industry built around using this kind of information to be able to do this. So, of course, it can be done. So the step in the process that I'm talking about today is getting from that data that you do have over to what the model needs. And we can make some simple assumptions. We can assume that there's no biomass coming into the plant, or we can assume it's a negligible amount anyway, and things like that. And we can assume that probably the dissolved oxygen is 0. But for the data that we do have, we need to sort of translate it from the total measurement into what the model knows. So I've attempted to put together a visual representation of what this means. And so this is a new slide that I'm showing you for the first time today. This is a way that I've always kind of seen it in my head, and I'm a bit of a visual kind of thinker, right? So if we measured a number of components and in our influent, and we say we have a total amount of COD, and we have a total amount of TKN and a total amount of phosphorus, what the model does, the model needs to know what all of those individual components are. So I have something that tells me, everything added up together is 400 milligrams per liter of COD. But we're going to have to break that down so that when the model sees that, it's broken out into all of its individual components. So you can see here that in ASM1, there are 7 kinds of COD coming into the influent. So we need to break this up. And as I said, we can make some reasonably safe assumptions about some of these, that they might be 0 or negligible. And then for the rest, we then have to make some sort of calibration of our model to adjust, put the right amount of the COD in the right bucket in order to make the model work the way that it should work. So basically, we're taking that COD and we're breaking it into a bunch of little pieces, and these go into the plant and they go into the model, and they're acted upon in the model, in different ways. The soluble substrate, this is the SS down here, the soluble substrate and the soluble inert, they of course float through, they're not going to settle out, but the particulate stuff will. And of course, the biodegradable things, XS and SS, will undergo transformation in the bioreactor as they are acted upon by the biomass. And here's some biomass that's coming in. I took a little bit of liberty with the proportions here so that I could actually squeeze some text onto these. But, very likely most of the COD coming into your plant is going to be SS and XX and XI. So, the 2 kinds of substrate and some particulate inert material. This soluble inert, which is basically not acted upon by anything, it's just going to float through the plant and go out at the end. You can estimate that from your effluent numbers. But the point is, this is kind of like a visual representation of what we're doing. We have one number, 425 milligrams per liter of COD, and we have to divide it up, but we don't know exactly what these proportions are. So we're going to use some of the information that we do know and some typical ratios in order to get us into the right box. And the story is the same for both nitrogen and phosphorus. Now, there are fewer things that we have to break them up into usually. So there's going to be, some organic nitrogen here, soluble particulate organic nitrogen. There's ammonia. And of course, there's a little bit of nitrogen that's stored in the COD that we have to account for. By the way, note that this is TKN measurement. So, of course, we don't have even some other kinds of nitrogen in here, like there's no nitrate, for example. So you might have an incomplete picture of your influent with respect to nitrogen. And total phosphorus is again the same deal. We have a couple of state variables for phosphorus, and then we have the amount that's stuck into the other COD. Now that's the tricky part. So the tricky part is that when I'm looking at this COD and I'm trying to move around and adjust the size of these chunks so that the model works the way that I want it to, we are actually affecting the amount of nitrogen and phosphorus as well. So this slab here is actually distributed according to some of these other state variables here, because there's a fixed fraction, a fixed ratio between the amount of particulate inert material and the amount of nitrogen that's associated with that, right? And you can adjust those. Those are parameters that you can make adjustments to in GPSX, but if you leave them as constant and you're adjusting the relative biodegradability by moving some stuff back and forth between substrate and inert material, you're actually shuffling a little bit of nitrogen around, and maybe some of it will end up more or less from your stock over here that ultimately will get distributed to the rest of the state variables. What ends up happening is in a lot of our influent models, we'll end up with saying, okay, we're going to specify the ammonia, we're going to specify XND, we're going to calculate all this stuff over here, and then whatever's left over by subtraction, we're going to stick it into soluble organic nitrogen. So there are a number of variables that work that way. We make soluble organic nitrogen the degree of freedom that will be calculated one way or the other. And there's also the same sort of deal for The phosphorus as well, and even the COD itself. Usually XS is kind of like the one that we dump all of the remaining COD into once you've specified everything else. So that allows us to have things that change and move, and it kind of goes into a spot that makes the most sense for the type of data that we're used to dealing with. And that's worked well for us over time. Okay, so we have to deal with the fact that we have these little slivers of nitrogen and phosphorus that are attached to our boxes of different kinds of COD, and as we move those around, things are going to change. Okay, so I wanted to show you that sort of visual representation of it because it is a bit of a hopefully a better understanding of how there's like a lot of moving parts in an influent characterization. Now, you don't have to generally worry about that almost like most of the time, right? Like generally, if you have reasonably good influent data, you type it into GPSX, everything's going to go in the right place and it'll calculate the leftover, put it in the appropriate place, and you're good to go. It's only when you get into like extremely not biodegradable or strange high concentrations or something where you might find that I've got to start making some adjustments. Or I have a very unusual influent for some reason. I've worked on a couple of projects in the past year where the data kind of looked normal until we put it into GPSX and we started getting a really good look at it. And it was like, well, this is really implying a very non-biodegradable influent, more than you might have expected. So anyway, those are always the interesting aspect of doing any one of these jobs. So the key thing that you have to do with your influent characterization is break it down. It's usually pretty straightforward to break it into, soluble and particulate components. Hopefully you have enough data to be able to sort of see that. And then try to break it into this readily biodegradable versus inert portions of your plant. So I've rearranged these boxes here to make another different kind of influence setup. We can see here, this one's got a lot of soluble substrate, a smaller amount of particulate inert. And, it's basically like sort of dividing the top from the bottom here and the left from the right. We're going to say basically we have lots of substrate in this one and not so much inert material. And this is biomass and cell products here. It's basically balancing the relative size of these boxes to each other is what you're doing. Okay. We have the input concentrations here on this side. And basically the top part here, before we get to fractions, the top part of this influent is the information that you have measurements for. Now, you're not going to have all of them, but this is the place that any measurements that you normally would have, you would put these in the top of this column here. So it's going to be your COD or BOD numbers, TKN, ammonia, phosphorus, VSS to TSS ratio. Those numbers are what goes in up here. The next section is also input, but these are numbers that you are probably not going to have data for. These are the ratios, like what is the soluble inert fraction of the total COD and what is the particulate inert fraction and so on. So these are important fractions. We're going to come back and adjust these and make changes to them after we go. But right now, what you usually do is you just start out with the data that you have and you leave these at the defaults, and then we can come back and adjust those as needed. This is also where you enter your pH and your alkalinity. And then from here down all the way to the bottom of the menu are what we would call basically everything else. And so these are almost always going to be left at the default or set to 0. A lot of the defaults are 0. These are basically the other components that are going to be probably generated in the plant, but they're not coming in the influence. So we set them to 0. So a good example would be struvite. It's not coming in the front of your plant, but it could be potentially generated in your digester. So that's why it's part of the model. We do mass balance around it, but it's not going to be in your influent. And this is the place you would also specify the biomass coming into your plant. And we also assume that's 0 or close to 0. So once you've entered in these numbers, automatically it is going to calculate all of those state variables like the ones I was showing you earlier. And these are basically the ones that the model needs to know. So we go from here via a series of calculations to get to this. and we can look at this, open up these panels and take a look at all the details. And then from here, we go to what we call our composite variable calculations. These are the ones that you probably do have measurements for. These are the ones that you typically are trying to match to some real data. So these are things like TSS and VSS and soluble BOD and so on. And all of these numbers here will change if you make any changes over here. So a couple other features that I'll be showing you here shortly. Anything that you can click on, it will highlight for you exactly how we calculate that. If you scroll down to the very bottom, you'll see the equation. Some of the equations can be quite long and detailed, but you can see that. And it also highlights all of the other parameters that are relevant in that equation. So here you can see our total carbon is calculated as being total organic carbon plus total inorganic carbon. So it shows you how we got those and how those numbers go together. And lastly, this is actually a very handy tool that we added right at the very beginning of the development of Influent Advisor, and that is these regular stoichiometric ratios that you probably would like to be keeping your eye on. And so it's sort of your nitrogen to COD ratios, phosphorus to COD ratios, VSS to TSS, XCOD to VSS, all of that kind of stuff is here that you can keep an eye on, and these will automatically be calculated from all the numbers that you have entered above. And one of the main features, the things that really is the main debugging help, is any place that we calculate something that is being calculated through subtraction. If it comes up to be a negative number, then we let you know. We put the actual negative number there, and then we highlight the fact that this is an issue, and you're going to have to change something in order to resolve this. So if we were to just set it to 0, then that would kind of break the mass balance of the calculations we are doing. So that's why we want everybody to sort of be aware that, yeah, the data you have has a problem with it. Really, we're going to have to change one of these other ratios in order to clean this up. So you can't even actually accept the menu and close it if there's still negative numbers showing. And it's very handy to be able to just click on this number and then immediately highlight all of the other parameters that are being used in that calculation so you can see what it is that you have to adjust. Okay, so as I was mentioning, we are going to have an option to choose from different types of Influent models. And by Influent model, what I mean here is a set of calculations, just regular algebraic calculations. It's just it's not the actual matrix model. We're not integrating anything. This is basically just a calculation to get us from the data that you've entered to what the model needs. And we've got them set up for different types of data. So COD states is the one that will automatically be selected for you when you drop your Influent object on the drawing board. But we can work with the BOD-based version. There's a TSS COD one, COD fractions, and so on. Almost all the work that I do in the COD states model. It's the one that I find is sort of the best calibrated. And I always really like to work with COD data every time I can. COD is conservative. It's what all the models are built upon. So it tends to work better for us than working with BOD data, which is a little bit more error prone. So, right. Okay. So just to show you explicitly here, this is the opening input menu for each of these 3 different kinds of models that we have. The COD states, that's our default. You can see you start with COD, TKN, and total phosphorus, ammonia, etc. Here's BOD. We start with BOD-based TKN, TP, and then you're into some other different things and different kinds of fractions down here as well. And we also do have this one, just threw it up here just for input sake. So you can actually specify your Influent to be a biosolids line. Like basically you could say it's thickened WAS or something. And up here you have TSS, you'd enter in, we have it as a default of 10,000 milligrams per liter. And, you would set some other typical numbers for that as well. So which one you pick is up to you. Influent Advisor works the same way for all of them. It's just a different set of default values. Okay, now is the time for the demonstration. Sorry, I jumped in one set of slides too early there. Okay, so what I was trying to say before was, first of all, here, you right-click on Go to Models. You can pick whichever one of the Influent models that you want to work with. As I mentioned, I work with COD states almost all the time. And you go to Composition, and you go to Influent characterization. And then now, as you can see here, we've got our inputs on the left and our calculations on the right. So I'm just going to change a couple of numbers here and there, and you can sort of see the activity. So right now, this is total COD up here. It's at 430. That's our default value. And as I change it, these numbers in the right-hand column over here will change because they're being calculated on these numbers, which are calculated from your inputs. So I'm going to switch this up to 600. So now we're going to say there's more COD coming in the influent, and all the other fractions will stay the same. And by doing that, we can see that our total suspended solids went up. Our total COD, well, that's now 600, the number I entered, and our BOD went up, and various other, everything kind of increased over here because now we've got more COD that we're dealing with, but we proportioned it out in the same way that we did before. So that's pretty straightforward. We can actually dig into the details if we want. So for example, I can open up this panel here, other particulate organic compounds. We can actually see how much particulate inert COD we have, 78 milligrams per liter. Here's our excess. This is the one that we calculate. This is our sort of leftover mopping up COD bucket here. This is all the other COD that we didn't specify for other places ends up going in there. Right. Okay, so I'm going to reset this back to the default 430. And what I want to do is change one of these fractions now. So this is where you would go in order to do a little bit of fine tuning of your data. So say you entered all this in and my total COD number is okay, but let's say, for example, my BOD number is too high, right? That means that if my measured value is lower, then that means that really my influent in reality is less biodegradable than what we've got set up here. So that easy way to do that is come in here and change the particulate inert fraction. So if I ramp this up, make it more inert, increase the inert part. Now, if I go back here, this number previously was 220 something, and now it is 150. So that's a way to sort of do your calibration. Now, if I had the whole rest of the plant built out, we would have also seen the mixed liquor change, and we would have seen the sludge production change, because now we got more of this particulate inert stuff hanging around. It's not being biodegraded very well, and it's accumulating, however many SRTs happen, and it becomes a significant part of the mixed liquor, right? So that is how changing your influent fractions will ultimately get your numbers where you need them to be so they match your real data. But then, of course, that makes it easier to get all the rest of the activated sludge part in line, right? Like, if you didn't make any changes here, and I was, leaving this at the default, and I just let all of that biodegradable stuff go into the plant, and then I'm trying to calculate and calibrate, the rest of the thing, solids settling and the biological stuff, you're starting off on the wrong foot anyway, right? So let's show you one example of where we're going to get some numbers that need to be debugged. So I'm going to reduce the total TKN from 40 to 20. And we can see immediately a couple things got highlighted in red here. So if we open those up, we can see that the nitrogen in the slowly biodegradable substrate, so that's a nitrogen associated with XS, is a negative number. And then also we can see here that number is being used in this number. And so therefore, we're running into problems, and this needs to be fixed. The reason it's like that is because our TKN is actually less than our ammonia. That's actually the main problem here, is this number that I changed. So that's a good thing it identifies. And if you did want to, as I mentioned before, you can click on these numbers. They immediately highlight where everything is. And you can see here that number that I just changed was one of the ones that's contributing to this problem. Okay, so I'm going to put that back to where it was before. This number returns back to a good value. And I want to click on, this is a really long equation, so I'm going to click on SND here. This is a little bit more straightforward to see. So that way you can, if we scroll down here, you can see we calculate SND as the soluble TKN minus ammonia minus the soluble inert material times its nutrient fraction here. So that's a way to sort of see what's going on. And as we mentioned, these numbers are highlighted above. So when we said INSI, that's this new N content of soluble inert material is here. Excuse me. Okay, so that's there. This stoichiometric ratios are right here. They're at the very bottom after all these numbers have been calculated above. Those are also helpful. And I will also point out a little bit of other functionality while I'm in here. We do have two different sets of default values for these things. Right now, this is raw influent, but if I click on the primary effluent number, we can see it overwrites the values with some new values that we keep as our defaults. And this is handy because, especially for the fraction section here, it gives you a better place to start from. You'll probably come in here and make some changes on top of that with your own numbers, but at least it sort of sets up the stoichiometry, maybe a little closer to what you have, and it'll make your life a little easier, very likely. Okay, so we also have a few other features down here. There's some global stoichiometric parameters that are available here. I will mention when you're looking at this menu, you are characterizing one single influent. And that means I can put many of those objects on the drawing board, and I can characterize them with all their own stoichiometry and their own concentrations. And you can combine them with the combiners, flow combiners as you go. We do have a couple of parameters, though, that are global, meaning one setting across all of the influence. So if I go here, plant-wide properties, one of the tabs is called Influent Characterization, and here's some global settings that you may want to come and take a look at if you're working with, potentially maybe your municipal wastewater's got, an industrial contributor, and it might be a little bit weird COD, maybe not typical household waste. So therefore, I may want to make a small adjustment to this ratio here. I would say a majority of the time, I never need to touch this menu, to be frankly honest. It's only when I get into like something other than regular, when we might have to come here and touch up some of these numbers in order to meet both our COD and our BOD together at the same time. We can also take any notes that you like here as well. Just open up a little panel. This is just like any of the other notes panels across various places in GBSX. We have our dynamic validation button. I'm going to come back and talk about that later. And of course, you can always export out your data here. So I'm just going to do that real quick. And where is it's opening up on another page? Here we go. And you can basically export all of this information that you have into an Excel spreadsheet, and it'll automatically save that for you. So just let me show you what that looks like. Sometimes this is the kind of thing you might want to generate and toss in an appendix at the end of your report, or have that as a supplemental resource for your projects. Okay, I'm going to keep that open. Well, no, I'm going to close that before we move on. Okay, so let's close that up, and I'm going to go back to the slides. Okay, so one thing that is a challenge every single time you sit down and put together a model is that a lot of the times the influent data is, less than perfect. That's not really, necessarily a problem all the time. It is just the nature of, the way that we collect data in this industry. There's a lot of noise that is associated with it. There's a lot of variability associated with the way that the data is collected, and so on. And so we have a lot of understanding of these things, and we're able to deal with that accordingly. However, it is something that you have to get used to dealing with. So basically, one thing I can suggest is really trying to find, if you're doing a simple steady state calibration of a model, is try to find in the say years worth of data that you've got, try to find a stable time period where there's not a lot of variability happening. You're not in a period where it's just coming off of an upset, or it's undergoing some changes due to, taking units out of service for maintenance or something. You want what you would call typical behavior. Give me a couple of months of when it was just running normally. And those averages and those types of numbers are probably where you want to start. Now, when you get into doing dynamic calibration, then you want to be able to see a little bit of dynamics to it. You want to be able to see something changing as you go, maybe from one season to another, and the temperature changes. Those are where you want to have a little bit of dynamics in it. But for steady state, and usually that's where you start from. Let's just make our lives simple and start with something that's a typical average behavior. So you're going to have to go through that data, and you're going to have to remove outliers and deal with the fact that maybe some of it doesn't make a lot of sense. You're almost always going to have some missing or bad data, or stuck data. I've had multiple projects where I open up a spreadsheet and you plot the data, and there'll be like a chunk of data where you get the same number for 4 weeks in a row. It's because somebody's sensor was off or missing or out of service or whatever, that kind of stuff. So anyway, filter all that stuff out, and then you're left with something that's a good place to start from. But often you have to deal with conflicting information. Right. Okay. So the way that you want to that you can identify that and get a reasonable level of comfort that the data that you're using is okay is to just calculate these various typical wastewater influent characterization ratios, and then you just see that they're in the range or near the range anyway of what you would expect for regular municipal wastewater. So look at your VSS to TSS ratio, your BOD to COD ratio. Is the COD, something in the neighborhood of 2 times the BOD? Is your ammonia less than your TKN? Is it something like 7.7 or something in that neighborhood? And your soluble to total COD numbers, do they make sense as well? We tend to always want to go through and do that on averages, but it's also great to take it and take a look at it on a point-by-point basis in your spreadsheet work as well. Those are nice typical things to get a handle on. I mean, individual data points, they're probably not that important. It's probably just a bad measurement, or if it was, maybe not sampled well on a particular day, or you caught it just in some sort of weird point. But if you have a consistent measurement that is always out or always, showing a relationship, then I would be skeptical of that data and go back and question it from the person who provided that data to you, because either A, you'll find out it's no good, or B, there will be a reason why it is weird. And so you will be able to at least get that reason and understand what's happening. Okay. So the way you typically go about setting this all up and then doing a bit of validation and further adjustment and calibration of your Influent is basically enter in all of those. Start with using the defaults from GPSX. Hit one or the other of those 2 buttons to start with. Then enter all of the known concentrations that you have in that left-hand column at the top, and then identify any flagged issues that come out of that. So go through and take a look at the middle column to see what the values of the various state variables are and make sure nothing's negative and that it all kind of was as you would expect. And if it isn't, then you have to trace the dependencies back to the adjustment to the fractions that you don't have data for, or the numbers that you do. And if you're willing to make adjustments there, then do that, and then make the changes to the stoichiometry in order to clean up and remove all of those flagged issues, and then see how that matches up with the other data that you have that you never entered. So you entered a COD number, but if you have a BOD number, does it match that number? So you can adjust that fraction like I did in my earlier desktop demonstration. So this is kind of iterative. And I know different people who have their own different preferred way of making their way through the data. A lot of the time it is really dependent on how much and what the quality is of the data that you have. But we're hoping that, this tool is one that will allow you to work through and do it as quickly as you can, whatever way that you like to do it. We've set up Influent Advisor to do the calculations right in the menu rather than having to run a bunch of simulations to see how it came out. We're doing it right in the menu so that you can debug all of that data before we get into actually running actual wastewater simulations. So basically what will happen is after you've gone through the step of setting all of this stuff up here, all of my concentrations that I know, then basically it's about adjusting these things, which we don't know, in order to match these numbers to the ones that you have data for. So, it's just basically adjustments and seeing if I can get reasonably close. One thing I always like to remind everybody is, especially if you have a lot of data, then you're probably taking an average that you're trying to match to over here. That average is going to, be an average of a bunch of numbers that have a certain spread on them, a certain distribution, certain plus or minus. So keep that in mind. Don't worry about trying to match it down to like the nearest milligram per liter, because there was a lot more data variability in your data than that to start with. So I'm providing this little chart here. This is one that we talk about a lot in our training sessions that basically is kind of a rough range of our experience, getting through calibrating a lot of models over the years. And you can see these ranges. These are actually the GPSX defaults here, 5% of total COD for the soluble inert material. But, 5 is the default, but the range from 4 to 10. And so these numbers are somewhat where you would expect them to be in a reasonable range. I should emphasize this is for regular raw municipal wastewater, right? So those are numbers that you can kind of use that to have a bit of a good feeling about whether the numbers that you ended up with make some sense. Okay, just to sort of wind up the context of why this is important. The experience that we've had and the entire industry basically shows that the default biological parameters in the ASM models, and by that I mean like heterotrophic growth rate and yield and whatnot, they don't tend to require much adjustment at all if the influent characterization is good. If you find that you are making, huge changes to your growth rates, then you're probably doing that to counteract for something that has not been entered into the influent correctly, or maybe not necessarily entered in incorrectly, but a lack of information on something about that influent. Like maybe you're ramping up the growth rate because actually there's less food in the influent than there was in reality. So what I always suggest is if you have to, a little bit of resources that you want to spend on getting good data, spend it on getting a good characterization of your influent. That will help a lot. Now, there's a whole other, this discussion that I've been doing so far actually segues directly into how to calibrate your GPSX model. And we already did a really good webinar on this last year. So I highly recommend you pop over to our YouTube channel, youtube.com/hydromantis, and check out this webinar that myself and my colleague Nick Piccolo did last summer. I think it's a really good one. I've actually kind of stolen a couple slides there to kind of the story continues over there on that webinar on how to calibrate the model. It starts with talking about what we're talking about today with influence, and then it goes into talking about calibrating other things like settling parameters and things like that too. Okay, one thing I will mention is that all of what I've discussed up to this point is for regular municipal wastewater. Industrial wastewater is a completely different bag. Often, anyway, it is a completely different bag. It really varies widely by industry. So you can often get very high concentrations, particularly high concentrations of COD or nutrients, and they can be either really nutrient rich or really nutrient deficient, depending on what that industry is. I know over the years, I've actually done quite a lot of modeling of wastewater treatment plants that treat waste from industrial food preparation facilities. It just sort of happens to be an area that I accidentally stumbled into. So I've done a lot of things with winery waste and dairy waste and breweries and fish processing and potato processing. So they're all wildly different from each other. And I find it really fascinating, to be honest, myself, but it makes for setting up your influent very challenging. What you might find is that you have to change those influent stoichiometric parameters a lot. Particularly if you have very high COD, like if you had, I remember one project that we had many years ago where it was a factory that made rice and pasta side dishes, and it had a very high COD. And it had, as it turns out, it was reasonably inert, which was also surprising, and also not very much nutrients in it. And in fact, I think the plant had to add nutrients before they were allowed to be able to discharge it to the municipal system. So my point is, when you're into industrial wastewater, all bets are off. You can do anything you want with the influent characterization at that point. You can set those fractions to 0 or 100% because it is very unusual waste. So, and lastly, it is a good idea if you know what they're producing. Usually the wastewater is pretty consistent if they're producing a certain kind of food product. So tying your influent characterization of what was being produced at that time is usually a good call. I will also recommend you to pop over and take a look at our modeling industrial wastewater inputs to municipal facilities. That was a webinar that I did last July. It was a really interesting one that I really enjoyed putting together. I talked about and showed some data from many different kinds of industries and how variable it all is. Okay, so now we're down to the last little bit that I wanted to talk about, which is what do you do if you have a large amount of dynamic influent data that you are reading into your model and your influent is changing over time? And that is, of course, a very valuable thing that you can do in GPSX. You can have a large spreadsheet with many rows and your concentrations can be read in and it drives the model dynamically. Of course, a lot of people do that for flow, but you can do it for all the influent concentrations as well. Now, all of the stuff that I've showed you so far is basically just a single snapshot of one set of data. So it would be, say, a steady state average of something. But when you're running the influent model, it, of course, is doing that on every step, every time step as you go. So how do I do that, right? That's not easy to like sit down and type in, every row of your spreadsheet into GPSX. So we actually have a special tool for doing that called the data validation tool. It's down at the bottom. It was that other button that I, mentioned earlier. Basically, it's performing Influent Advisor on every row of a spreadsheet and then getting out another spreadsheet that gives you all those results. So I'll show you what that looks like right now. Okay, so here we go. I have a spreadsheet already set up and ready to go for the demonstration. So let me open that up for you first, just to give you a little feeling for what I'm talking about here. The reason this is really useful is that it is, of course, very difficult to see sometimes just by looking at raw data, whether it's going to be problematic or not until you actually run it through the simulator. So just let me show you. Here's a spreadsheet that I have. So it's time in the left-hand column. So we actually have 600 rows of data, and we're reading in COD, total phosphorus, soluble phosphorus, and flow, right? So you can see here that these numbers vary quite a bit. It starts at 390 and it goes up to 400 and something, and then it comes down again. It's pretty tough to just sit here and look at these numbers and know whether they're all okay or not. So I'll show you that we go down here like 600 rows. So, okay, so it's a lot of data to sort of take into account. So what we're going to do is we're going to use this button here. I personally feel is like one of the most valuable things that we've hidden away in a button in the corner of one of our menus. It's probably very invisible to people. Input file. So that I'm just going to browse to that file that I just showed you. Oh, what's going on here? Come on. There we go. So that's test data. And then we have to then produce a new version of this, another output spreadsheet. And it's called, it gives you the name data validation. You can change it to something else if you like. So I'm just going to save that. And then we hit this button. So basically, this is going to take like 15, 20 seconds where it goes through, reads in a row, does a complete set of influent characterization calculations, checks everything, may see if there's any negatives or anything that we need to warn any about. It does a bunch of coloring of the spreadsheet, and then it moves on and does the next row, and it goes all the way through to the very end. So that's going to take a moment, and I'm just going to take 1 second here to drink a bit of water. All right. Oh, okay, done. So what I want to do then is I want to open the spreadsheet. Let me do that. And here, this is what it looks like when it's done. So this has now produced another different spreadsheet, and you can see the calculation of all of the state variables. So this is essentially the middle column of Influent Advisor. And then if I keep going to the right, we will get to the right-hand column. This is basically all of the composite variables. So there's like dozens and dozens of rows. It produces a lot of output, right? Okay, so now I know I used a particular data set because I knew it was problematic. We can see here that if we go down a little ways, it highlights in red when some stuff comes up negative. So this is the state variable for phosphorus that's in the particulate slowly biodegradable substrate. during some periods of time, all of the inputs we were using resulted in some negative numbers. So it immediately says all of these rows are a problem because one of the states came out negative. And in fact, if I go down farther, there are a number of other ones here too. And we can see there's some more phosphorus ones. This is actually SND. This is a soluble organic nitrogen. So that's another time when some calculations for nitrogen came up, and so on and so on. Now, the reason is because we were only changing 2 or 3 inputs from line to line, and we were holding all of our other stoichiometry constant. So what this means is that maybe we need to actually have a dynamic column where we change the stoichiometry, or maybe the default value that we were holding constant was a bit too low or too high, and therefore we could make adjustments to that. Nonetheless, this is the tool that's there to point you to the specific rows in your sheet that are the ones that are a difficulty for you. Okay, so I'm going to pop back to the slides to kind of wind things up here. A few final thoughts. Basically, starting with setting up your Influent characterization, you got a bunch of different model options. Basically, you can choose based on whatever Influent data that you have to start, and we always recommend COD states. It's the default one. And Influent characterization is certainly a key to doing a good model calibration. You will find that it will make your life go a lot easier if you just take a good look at your Influent data and make sure everything is in good shape before you use it. And as per always, use Influent Advisor. That tool helps you visualize all your data issues, and also do those ratio checks as well. That is also a good thing to do right even before you start entering stuff into GPSX, because you don't want to start off with data that's going to be difficult for you even before you get going.